Okay, we'll wait 3 more minutes. While we are waiting, if you go to the website, I'll link it to you once again now. And on Show My Homework, we've put on electrolysis stuff, which is chapter C6. But I sort of thought that maybe it might be a bit difficult because it requires prior knowledge of something that you did all the way back in year 9, which was the chemical changes topic. So if you've forgotten all that stuff, which naturally you would because that was way back in last year, I just wanted to have a quick recap of writing ionic equations and writing half equations because you need that to be able to understand what is going on in the electrolysis topic. Otherwise, it would just be complete gibberish to you. So for this topic, it is important to have a little bit of background knowledge. But first, we're going to start off with opening up the higher tier booklet. Once again, there is going to be a Word document for you guys in case you want to type stuff in, but there's not really much like note taking. It's mainly just practice in this topic. So let me just open up my version so I can write on it. Okay, so just as a quick recap of what you guys did back in year 9 is you were introduced to this major keyword known as reactivity. So that is a hugely important keyword that comes up again and again in chemistry. And it's sort of how, in chemistry, is how we describe how easily or even violently a substance will chemically react with another substance. So it's how easily or violently a substance will chemically react. So for example, if you had a chemical that during a reaction causes like a huge explosion, we would call that, oh, that chemical is very reactive. Or if we just put a substance and chemically reacted it and it just formed like a few bubbles, we would say, okay, that's not very reactive. And you would have also been introduced to this chart, which is basically the order of reactivity of metals. However, there are 2 non-metals here that are also included in this list. The ones at the very top are going to be the most reactive, and the ones at the very bottom are the least reactive. Just to save space, I've put on the chemical symbols, but remember, you'll always have access to a periodic table, just so then you don't actually have to memorize all the chemical symbols. I'll pull up a GCSE periodic table for you guys now to have on a second monitor. AQA. Oh, here we go. There we go. I've just linked the AQA periodic table now. Let me just check if there is. Yes, there is a rotate option at the very top. You might want to rotate that just so then you don't have to tilt your head in order to read it. Okay, so we have the symbols there. When it comes to memorizing the order of reactivity, AQA does expect you guys to be able to memorize this, and I don't want you guys to feel like completely overwhelmed because 95% of the time, they probably won't ask, for example, which is more reactive, magnesium or aluminium, which were these two by here. Like, they're not usually that evil. Usually they'll just sort of ask for the general thing, like for example, what is more reactive, lithium or copper, things like that. Or what is one property of copper? Oh, that is very unreactive. So it's more so a general idea of where things are. Obviously, if you have time, the best thing to do is memorize it, but I don't want you guys to stress out about needing to memorize it straight off the bat. Right now, I just want you guys to get used to where things are placed, and not so much focus on the tiny little differences. So in general, know, for example, that the group 1 alkali metals, the ones on the far left column of the periodic table, such as potassium, sodium, lithium, they're all quite reactive. Group 1 alkali metals are quite reactive. Things like silver and gold are unreactive. We have like a lot of elements in group 2 are less reactive than group 1, but still quite reactive, such as calcium here, magnesium here, and so on. So I just want you guys to have a general idea right now about the order of reactivity, and memorizing it fully is almost like a cherry on top, because it's unlikely that they'll actually ask you to just duplicate the list. But if you do want to have a go at memorizing it, I did find like a mnemonic online, which is basically help with memorizing the key main points. I have bolded here the list, so please stop like calling me a careless zebra. Instead, try learning how copper saves gold. So it is it's quite a silly mnemonic. If you find a better one online, please do let me know, just because this is the best one that I could find, that when you say it out loud, it is easiest to memorize. So that reflects potassium, sodium, lithium, calcium, magnesium, aluminium, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold. So that is the order of reactivity. Remember, memorizing it is just the cherry on top. So don't stress out about memorizing it too much. So one thing that happens due to the fact that some metals or some elements are more reactive, more likely to chemically react than other substances, is we have what are known as displacement reactions, meaning one more reactive element kind of bullies out and takes the place of another less reactive element in a compound. So if you imagine, say, we have, I'm going to draw this out. We're going to call this potassium. I'll just write K to make it easier. So this is potassium. Potassium has huge muscles. He's very reactive. And he comes across, let's pick copper. He comes across copper. And copper is bonded to let's say a sulfate. This is copper and this is sulfate, SO4. So copper is bonded to sulfate, and what's going to end up happening is that potassium is going to kick copper out of that reaction. This deserves to go into a museum, really. And is now bonded to our sulfate. And then copper is left on his own. So that drawing is a displacement reaction, basically. Okay? So we have a more reactive element, potassium. We have a compound of a less reactive element and a non-metal compound. And then the more reactive element takes the place of the less reactive element. And then now the less reactive element is off on his own. Okay? So that's the main thing that we are looking at in a displacement reaction. So if I were to summarize it in notes, let me rub off my drawing here. What a shame. If I had to summarize it in notes, I would say more reactive element takes the place or displaces less reactive element. In a compound. And this has quite a few uses, because if we have, yes, Sophie, basically what we're going to be doing is we're going to have a little bit of practice in a second, but I'm just giving a bit of background at the minute. Okay? Right. So the main uses of displacement is, say I wanted to extract copper. Copper is bonded in a compound, but I wanted pure copper. Well, if I chemically react it with something more reactive, then solid copper would form. So that's the way we extract elements. So if we wanted to extract an element from a compound, such as making pure copper or making pure aluminium or whatever the case may be, we react that compound with a more reactive element. So then that way we can extract it. Now we're going to move on to what is only on higher tier. If you're in set 1 and set 2, you would be placed in doing higher tier, because you guys are capable of doing it, even if it seems hard at the start, okay? But the main prerequisite for doing these, what are known as ionic equations, is you have to know how to write an ionic compound, okay? So this is just a recap. If you're in my class in Double Award Set 1, we would have just done this right before we had to leave the school. Okay, but this is just a quick recap. Remember, okay, when it comes to what ions are, it's when a substance gains or loses electrons. So ions plus or minus electrons. I'm going to write E negative just to write it for short. So ions are when you gain or lose electrons, and then that gives a charge, because electrons have a negative charge. So if you gain an electron, if you're gaining a negative charge, it becomes negative. If you're losing electrons or you're losing this negative charge, it becomes positive. And when you form an ionic bond, remember it's all to do with gaining and losing electrons. So remember that when it comes to to writing an ionic compound, like for example, let's say that I had magnesium chloride. So this is my example, magnesium chloride, and I wanted to form symbols to represent magnesium chloride. Well, remember when it comes to symbols, sometimes you have like a little number at the bottom, such as H2O, and that little number tells you how many of the element just to the left there are, okay? So when I write magnesium chloride, I look at my periodic table, I see that my symbol for magnesium is Mg, my symbol for chloride is Cl, but I don't know if that's right yet, because I don't know how many magnesiums I have, and I don't know how many chlorides I have. The way I figure that out is by looking at what type of ion it forms, what type of charge it forms. Hopefully we remember this from before the break, but if I divide it into a list of positive ions and negative ones, group 1, what type of ions do they form? What charge are they going to have? Do we remember? Group 1 elements, they form a 1 positive charge. Group 2, can we guess what they form? Two positive charge. Okay. And there are also some other things that are not just an element, but an actual compound where the whole thing has a charge. So one example of that is you can have an NH4 compound and the whole thing has a 1 positive charge. So that is known as ammonium. For negatives, if we go on the right-hand side of the periodic table, these are my non-metals. So remember, group 0 is the one all the way on the right-hand side. They don't really form any charges because they already have full outer shells. So we'll start with group 7, the one that is just the one from the last column. They form a 1 negative charge. And then group 6, 2 from the last, are going to form a 2 negative charge. And then we also have other compounds. Yes, you do need to learn the charges of the compounds. Then you have other compounds such as the sulfate, which is SO4 with a 2 negative charge. One common mistake is don't get that confused with sulfide, which is just sulfur. We have nitrate, which is NO3 and then a 1 negative charge. And those are the main ones that you have to know. The rest, so the only ones that you have to actually memorize is the ammonium, the sulfate, the nitrate. The rest, you just check what group they are in the periodic table, and that's it. You don't actually have to memorize magnesium as a charge of +2. So to go back to my example, magnesium chloride. If I look at my periodic table, I see Mg, magnesium is in group 2. Let me just rewrite it down here. So magnesium chloride It's in group 2, so my magnesium is going to have a charge of 2+. My chloride, which is chlorine, is all the way in group 7, and group 7 has a charge of 1-, so it'll be MgCl-. When things form together in ionic bond, the overall charges are going to have to balance each other out. So my magnesium has a 2+ charge. My Cl has a 1- charge. That means in order to have these balance, I need 2 Cl- in order to balance out the 2 positives. So my overall compound is MgCl2. Another way I like doing it, because it works every single time, instead of needing to work out the maths, is if I rewrite it like this, I like to cross it over, take the number and cross it over. So this is just 1, and we don't usually write the 1, so Mg, take the 2 over, Cl2, and that works every time. But if you end up with the same number, then it's a 1-to-1 ratio, and then you can just divide it out. So for example, if I had Mg2+ and let's say O2-, and I cross it over, Mg2O2, because I see they're the same number, I just take it down to 1-to-1. It's entirely up to you how you want to do it. If you're more confident with this way, by all means go ahead. If you like the foolproof method, then you can use the cross method, and that's completely fine. Okay, so that was just a recap. Now we're going to move on to writing ionic equations. What ionic equations are basically like chemical equations that use symbols, but they show the actual ions instead of writing it so they actually show the charges. So in my example on the left-hand side here, this is generally what an ionic equation looks like, where you actually have the charges shown in the equation rather than just a simple balanced equation. Okay, I'm going to work on this one with you guys, the practice one, but I'm going to also use the example just to show you what I mean. Right, now for an ionic equation, what I always want to start off with is making sure I have a word equation. So I want to write out a word equation to start off with. Otherwise, it's going to be really difficult because I don't have a base structure. Jumping straight from this question to writing that, no matter how clever you are, that is going to be difficult unless you have a base structure to work from. So, to start off with, I'm going to write just a word equation to show a displacement reaction between zinc and iron sulfate. Remember when you see these Roman numerals here, that means that it's the charge. So for example, zinc Roman numeral 2 means zinc with a 2+ charge. But first off, I'm just going to write a word equation. So from the question, my reactants, the one on the left, are going to be zinc 2 and iron 2 sulfate. So I'm going to write zinc 2 plus iron 2 sulfate. And then what does that make? So think back to displacement. Okay, think back to displacement. Zinc is more reactive than iron. It's higher up on the table. So, is zinc going to be able to bully out iron and take the sulfate away? If zinc is more reactive, so it's a bit stronger than iron is, it's more reactive, can zinc bully out the iron to take sulfate away? Yes. So, if zinc bullies out the iron, that means that zinc will become zinc sulfate. And who gets left all on his own now? Write in the chat who gets left all on his own. Iron, very good. Yes. So basically, we have the more reactive element here. Oops. We have the more reactive element. Let me just find a good font. Bullies out the less reactive element, takes away its bond, its partner, and now left all on his own is the less reactive one. Okay, so that is my word equation, my main structure that I'm going to work with. Now the next step is to turn this word equation into symbols. Okay, that font. So zinc symbol, I look at my periodic table. Can you guys tell me what zinc symbol is? Zn, very good. So all I'm doing is just changing this word equation into symbols. That's it. So zinc is Zn. Is zinc, if I were to write the state symbol, is zinc solid, liquid, gas? Erin, if you have a look here, I'll link it to you again here. There's a periodic table. Yes, you would get it on the exam, so don't worry about memorizing every single symbol. What I've linked to you is the exact periodic table that you will receive. So zinc, what kind of state symbol should I give it? So S, L, G, solid, liquid, gas. What is it for zinc? S, very good. So I'm going to write that zinc is solid. Now I'm going to work on my next thing. So zinc, I turned it into a symbol. Now I'm going to turn iron 2 sulfate into a symbol. Iron 2 is iron with a 2+ charge. And sulfate has a 2- charge. So iron sulfate. If I were to write it out without the charges, it would just be FeSO4 because the charges already balance each other out. Okay? So we have iron sulfate, FeSO4. And because this is an ionic compound, remember that ionic compounds always actually dissolve. The state symbol we use when something dissolves is AQ, which stands for aqueous, meaning it can be dissolved in water. So I'm going to write the state symbol AQ for an ionic compound to show it's dissolved. Anytime you see an ionic compound, that means it can be dissolved and it would have the symbol AQ. Now that makes zinc sulfate. Zinc 2. Sulfate is, zinc is 2+. Sulfate is 2-. So zinc sulfate would be ZnSO4. plus iron. Oh, sorry, I should write AQ plus iron, which is Fe, and then the state symbol for iron would be S to show it's a solid. So all I've done is I've written out my word equation, and then I've turned each individual section, like I haven't changed the structure, I've turned each individual section into chemical symbols instead. Okay? Just from using the periodic table and also knowing that sulfate was SO4 with a 2- charge. Now, because the AQ compounds, the aqueous compounds, are dissolved, that means that it gets split apart back into its individual ions. Remember when we learned about ionic bonding, and you guys also did a prac to show that when you had table salt and you dissolved it, that can actually conduct a charge because all of the ions are moving around. All of the charges are able to move around. So when you dissolve an ionic compound, it gets split up into its individual charges. So anytime I see something that is AQ, I'm going to split it back up into what its charges are. So we have ZnS. That is an AQ, that is an aqueous, so it's going to stay as is. But then the FeSO4, that gets split back up into its charges. So Fe 2+, I got the 2 from in the question because it says iron 2. Fe2+, that's dissolved, plus SO4 2-, that's dissolved, arrow ZnSO4, Zn2+, that gets split as well because I see aqueous is split, plus SO4 2-. And then iron at the very end is not split because it's still a solid. Okay, so I started off with the word equation. Then I changed it into chemical symbols. Then anytime there is an ionic compound, that means that it got dissolved, so it got split up into its individual ions. That's where knowing the charge comes in. And then if you notice, on the left-hand side of my arrow, or at the top I should say, because I didn't have enough room, on one side of the equation I have SO4 2-, and then on the other side I also have another SO4 2-. What that means is that the sulfate ion, the SO4 2-, nothing actually really happened to it. It was the same on either side. So what I could do, because it's on the same on either side, is I could just cancel them out. And that ends up, if I rewrite this without the sulfate, it's Fe2+ aqueous, arrow, Zn2+ aqueous, plus Fe solid. And that is my ionic equation. We're going to do another one together just because I know this is quite difficult. But just to recap what we do, write out the word equation, turn it into symbols, then split up any ionic compounds because they got dissolved, and anytime you see something that's the exact same on either side, you can just cancel them out and then rewrite it out. So let's do another example. Okay. Let me think. We'll have go Mg. Okay. CaOMgO. Whoops, sorry guys, I'm just trying to find where I was. Okay, MgO, right. Okay, so calcium. I'm going to use an example of calcium plus magnesium oxide, arrow. Let me write this smaller so I can fill it all in one. So write this down, please. Calcium plus magnesium oxide, arrow. This is a displacement, calcium oxide plus magnesium. Okay. Now, first step, turn into symbols. So my calcium, I'm going to look at my periodic table, has a symbol of Ca, and it's on its own, meaning it's just a solid. The magnesium has a symbol of Mg, but it's paired with an oxide. Magnesium is in group 2, meaning it has a charge of 2+. Oxygen is in group 6, meaning it has a charge of 2-. So they're just going to balance each other out at a 1-to-1 ratio. And because this is an ionic compound, it's going to be aqueous. And that's going to make calcium oxide. Calcium is also group 2. So it's also going to bond with oxygen at a 1-to-1 ratio. And because it's also an ionic compound, it is also aqueous. And then we have magnesium now kicked out of the compound all on its own. It's just a solid. So anytime you see a compound that's ionic compound, that means it got dissolved, because it can be dissolved. It's aqueous symbol. Anytime you see just the element on its own, it's either solid, liquid, or gas. Because these are metals, they're solids. Okay, now the next step is split aqueous compounds. So, my calcium, my solid, isn't aqueous, so I'm going to leave it as is. My MgO is aqueous, so I'm going to split that up into its charges. So we have Mg has a 2+ charge. O has a 2- charge. Arrow, I might not have enough room, so I'll write it at the bottom. CaO, Ca has a 2+ charge. And then O has a 2- charge. And then Mg's not an aqueous, so I'm going to leave him as is. Right, now here's a task for you guys. If you look on the left, or actually at the top, so these are my reactants. And then this is my compounds, my right-hand side. Is there anything you can spot that is exactly the same and could cancel each other out? I don't mean just the same element because there's slight differences. I mean exactly the same. Let me know if there's any ones that you can spot. Spot on, the O2 negative. So the O2 negative, I could just cross them out because they're all the exact same on either side of the arrow. So they can just go. Now, if the last step is to rewrite after things have been cancelled out. So I'm just that's all I'm doing now. I'm just literally just rewriting it without my O2 negatives now because they were cancelled. So CAS plus Mg2 plus aqueous, arrow Ca2 plus aqueous plus Mgs. And that is my final ionic equation. Now, as a bit of practice for you guys, if you go on the website that I linked earlier, you click on Lesson 1, Ionic Equations. That's loading up. You should have this sheet. You don't have to print this off. You could just do it on a separate piece of paper. But I have this like sort of ramped up in challenge. The very first section where it says write ionic equations for the following balanced equations, I've already, written it out in chemicals for you guys, so you don't have to worry about that. You can jump straight into going from step 2. So you don't have to turn it into symbols because I've already done that for you. So don't worry about turning it into symbols for the first section. For the second section, I want you guys to balance it first, just to practice balancing. For the third section is going from the actual word equation, which is what we've done in this example here, going from a word equation. So the first, I need to close that. The first section, just from the start, write ionic equations for the first following balanced equations, 1, 2, 3, 4. Have a go at those. But I think we went over the scheduled time a little bit. So 20-minute break, and then you guys can get started. Or if you want, you can get started now. But in around 20 minutes time, I'm going to leave the stream on though. In about 20 minutes time, I'll go over, I'll be available for any questions. And I'll also be going over the answers just to the first section, so you guys have a clear vision of what you're doing. And then once you've checked your answers for the first section, then you can practice the challenges. The challenges, the middle and the last bit, are more of the same. They're just a bit more challenging, but I would be really happy if you managed just to do the first 4 at that time. So what you need in order to do this is you need to have the periodic table up, which is in the linked in the comments. So you need the periodic table up, and you also need to, I'll actually leave this up here. You also need to know in the periodic table which groups form what type of charge, and that ammonium is NH4+, sulfate is SO4 2-, nitrate is NO3-. So that I'm going to leave that up for you guys, so you can remember what charges what makes. Okay, so once again, the first 4 on that sheet, I'm happy if you managed to do that, but if you want to just challenge yourself a bit more practice, the next 2 sections. Okay, so we're going to take a quick break, but I'm going to leave the stream on so it doesn't chop in half, and I'll be back at 11 o'clock, so around 18 minutes time, just to go over and answer any questions as you're going along this. Okay, I am back, but just 1 second because I can't find my pen thing to go on the to write. Okay, I found it. All right, so this is quite challenging. So let me just do some of the questions with you guys, and then hopefully we'll be able to eventually do it together. So it is one of those things where the more examples you see, the better we are at doing them. So just have a pen ready so you can do these along with me. All right, so we'll start off with the first one. Mg plus H2SO4, arrow MgSO4 plus H2. Now, in that balanced equation, I haven't actually added the state symbols, which might make it a little bit harder, but just remember that when something is solid, or like when something's on its own, it's not dissolved. When it's an ionic compound, then it is dissolved. So such as H2SO4, MgSO4, those would be actually dissolved. Okay? Now remember, the first step is to split up anything that would be dissolved. So compound, compound, those two would get dissolved. Everything else would stay the same. I'm going to add the state symbols on now. So Mg is magnesium, that's a solid, and that's staying the same. And then the H2SO4 gets dissolved. Hydrogen, because it has the one electron only, it forms a 1 plus ion. And because I have two of them, I'm just going to write that there's two of them there. And that's dissolved, so I'm writing AQ. And then the next half of that compound is that SO4. If we look back onto our list, I'm just going to add hydrogen on here. If we look back on our list, SO4 is a 2 minus. And that's also dissolved. Then the Mg gets dissolved. It's in group 2. So that's going to make a 2 plus. And then the second half of that compound is an SO4. That's going to be an SO4 2 minus. And then hydrogen is at the end as a gas. Then the next step, if we remember, the next step was to cancel out anything that you see that is on this like opposite sides of the arrow. So if you spot anything on one side of the arrow, my arrow's here. For those of you who can't really see, there's my arrow. So I'm going to look at all of my things on the left-hand side. I'm going to look at all of my things on the right-hand side. Do we see anything that is exactly the same on either side that can get cancelled out? I'll wait and give you guys a second to think about what can cancel. spot on. So the way you can have a look is, I'm going to look at Mg, right? There's no the Mg here. There's no other Mgs on this right hand side. So that's not going to cancel. My H+, there's no H+ here on the right hand side. So that's not going to cancel. SO4 2-, well, I see another SO4 2- here. So that can cancel. And then that once again leaves us to just rewriting this, but with the cancelled thing left out. So we have MgS plus 2H plus AQ, arrow, Mg2 plus AQ plus H2 gas, and that is done. We'll do another one. Let me pull it up. Okay. The next one is, I'll do in a different color. Li. Oh, that color's hard to read. Do in white. 2Li plus 2HNO3, arrow 2LiNO3 plus H2. So, once again, I look at my two compounds. I look at where my compounds are at. Those are ionically bonded. So that means that they're going to dissolve. So which are going to dissolve? I'll let you guys have a think about which chemicals I'm actually going to end up splitting up in to show it's dissolving. Remember, the things that get dissolved are the compounds. The single elements on their own, they're just fine, but it's the ionic compounds, just like table salt, that can get dissolved. So anytime you see this compound in an ionic equation, and see a compound in an ionic equation, that's what's going to get dissolved. So there's two things on here, two chemicals that get dissolved. Write in the chat which ones they are. I'll scroll back up to the other one we did. So in this case, the one we just did, I see my compounds was the H2SO4 and the MgSO4. Those are compounds. Elements were just the Mg and the H2. And we ended up splitting and dissolving these two compounds. So because we split those, which ones do you think we're going to split here? Okay, so we are going to be splitting the two compounds here. So I know that these are compounds, so they're the ones that are going to get split. Anything that's an element on its own, well, you can't really split the elements, so we're going to leave them as is. So the 2 Li, lithium is a metal, so that means it's solid. And the H gets split from the NO3. So we have 2 H's, that means we have 2 H+, and that's aqueous. We have 2 NO3s, that's nitrate, that has a charge of 1 negative. I'm going to draw my arrow. Lithium nitrate is also going to get split. Lithium's in group 1, so that gets split into Li plus and NO3 minus, and then the hydrogen is just hydrogen gas. Now the next step is for you guys to think about what gets cancelled. So have a look at both sides of our equation and see if there's anything that is exactly the same on either side. So I'm looking at, first I'm going to look at the lithium, the solid. Well, there's no duplicate on the other side, so that's not getting cancelled. Looking for an H+, none on the other side, that's not getting cancelled. My NO3, yeah, I see an NO3 on the other side, so that's going to be the one that gets cancelled. And then the final step, once again, is just to rewrite this out without the cancelled ions. And then that's it. Okay. So, next one. 2Al plus 6HNO3 arrow 2Al NO3 3 plus 3H2. Now decide what is going to get dissolved. The compounds are going to be the ones that get dissolved. The regular elements, where it's just one particular symbol on its own, those are going to stay the same. So the compounds get dissolved. So if we spot what my compounds are, my compound is here and here. So those are going to get split up. Everything else will stay the same. So I'm writing my 2 aluminium. Aluminium is a solid. My H is going to be H plus. Writing AQ to show that it got dissolved. My NO3 is 1 negative. Writing AQ to show that it gets dissolved. Aluminium, because this is balanced with 3 nitrates, I know that aluminium, and it's also in group 3, is going to be a 3 plus. And then, oops, because I have 2 lots of 3, I have a total of 6 nitrates. And that's 1 negative. And then my hydrogen is just a gas, it didn't get dissolved. Once again, look for what can be cancelled out on either side. My aluminium, there's no aluminium salt on the other side, so that's not going to get cancelled. H+, there's no other H+ on the other side, so I'm going to leave that as is. My 6 NO3s, that matches up with the 6 NO3s on the other side. So I'm going to get rid of those. And then rewrite it out. Next one, the Fe. My compounds, iron isn't a compound, Fe is just the element itself. My HCl, that's a compound, so that's going to get dissolved. FeCl3 is a compound, that's going to get dissolved. H2 is just the element hydrogen, so that's going to be as is. So we have 2 Fe plus, and then we're going to split this up. H is going to be what's H going to be? H is going to be H plus. And chlorine group 7 is going to be Cl minus. Then to split up my FeCl3, because I know my Fe is balanced with 3 chlorines, and each chlorine has 1 negative, what do you think my charge on my Fe is going to be? How many positives do I need to balance out the negatives coming from the chlorine? Okay, so 1 chlorine is 1 negative. 3 chlorines, that means there's a total of 3 negative charges. So if I have an iron balancing it out with 3 chlorines, what's my charge on my iron going to be to balance out my 3 negative chlorines? Three positives. And then my hydrogen, oh, sorry, I forgot my chlorines. Because there's 2 lots of 3 chlorines, how many total chlorines do I have in this section here? I have 3 lots of 2 chlorines. Think back to just counting atoms. How many chlorines do I have? Six chlorines, and they're all with 1 negative charge and leaving hydrogen as is. Okay, now my looking for what can cancel. Fe, there's no just Fe on the right hand side. H, there's no just H on the left hand side, right hand side. 6 chlorines, I have 6 chlorines here. They can go. And then I just write the rest out. Okay, so what we will do, I'll balance the other, I'll write out other ones for you guys to do on the screen for some practice, and then I'm going to come back to just check how you did on the first one. So instead of having you guys balance, I'll just quickly balance it just so then we can get a bit more practice on these ionic equations, because they are challenging, they are hard. So don't feel bad at all if we are struggling, but once you guys understand it and just practice it over and over, it's like maths kind of. If you just practice over and over again, it will start to become a lot easier. Let me just quickly balance. Yeah, it should be the first one, Mg. I'll number these. Mg plus. And the second one, hang on. Something H2. Oh, this is actually a hard balance. Hold on. Put 2 there, 2, 4 lots. 4. Yeah, there we go. Worked it out. 4, 1, 4, 2, 2. Fe plus. No, that's not right. Hold on, I'm just going to quickly skip that one. I'll come back to it later. I'll write out the second one for you guys to do. Okay. 2K plus H2S. Okay, so for those three, have a go at working those out. Remember, hydrogen forms 1 positive, nitrate forms 1 negative, sulfate forms 2 negative, and then potassium is in group 1, magnesium is in group 2. And then I'm just going to have to ignore my attempt to balance this last one. 2. Ah, got it. Okay. So have a go at those 4. Have a go at those 4. Remember to, if you do the first one and you want to write out what you've done, just for me to check that you've done it correct, feel free. Or if you're stuck or as you're going along, you're unsure of a particular step, that's fine. But remember, first, decide on what you're going to be splitting. The things that are compounds, those are the ones that are going to get split. The things that are just the elements just stay the same. After you've split the compounds into its charged ions, then you're going to find any ions that are the same on both sides, cancel them out, and then rewrite it. So 3 steps: split the compounds, cancel out any ions that are the same on both sides, and then step 3, rewrite it. So I've written the charges in the chat for you guys to be able to see. The charge on H plus is the charge on hydrogen is 1 plus. Charge on NO3 is 1 minus. Charge on SO4s are 2 minus. Everything else you can find on the periodic table linked in the chat because they are in groups. And I will draw a sticker with the name of whoever finishes question 1. That's my sticker. Your name will go on it. If we finish just the first one, we seem to be struggling, so I'll just do the first one for you guys, and then the sticker will go to whoever finishes the second one. Okay. So Mg plus 2HNO3 arrow MgNO3 2 plus H2. All right. Split up the compounds. I have a compound here, and I have a compound here that I'm going to split into its charged ions. Everything else will be the same. So my Mg, I'm gonna leave out the state symbols just so it gets less messy, so hopefully we can see it a bit more clearly. Mg stays the same. My H is gonna get split from the NO3. My Mg is gonna get split from the NO3 too. I have an H that is gonna become charged, and hydrogen H's form a 1 positive charge. So I'm going to keep that coefficient because I have 2 hydrogens here, but I'm going to write that they have a positive charge. Because that 2 belonged to the entirety of the compound HNO3, that means I also have 2 lots of NO3s. And nitrates, NO3s, form a 1 negative charge. Then I'm going to work on my magnesium, my magnesium nitrate. Magnesium is in group 2, so it's going to form a 2 positive charge. And then that 2 on the outside of that bracket, that means I have 2 lots of NO3s. And once again, NO3s form a negative charge. And my H2 is just 2 hydrogen atoms combined. So that's not an actual compound, that's still just an element. So I'm going to leave him as is. That's sort of the hardest part, I think, about this, being able to split the compounds up into its individual charges, because you need to remember what forms what charge. And then now here comes the part where I look to see what can cancel. There's no just Mg on both sides. There's one on the left, but none on the right. There's no H plus on both sides. There's just one on the left, none on the right. But there's a set of NO3 minuses on both sides. So they can just cancel out. And then we're left with just rewriting it and that is my final ionic equation. So now try questions 2. The goal is to at least maybe be able to get one correct. So think about what you're splitting up, the compounds. Split it up into its individual charges. Then cancel any ones that are on the same on either side. And then rewrite it with the canceled charges missing. So the next one, remember that SO4 makes a 2 negative charge. Mick, a little bit close, but the charge on your potassium on the right-hand side, you've written it wrong. Okay, so that's good enough for me for a sticker. So I'll rewrite it out just so then you guys know what Mick has done. I gotta redraw my sticker. We'll go with Galaxy. We'll go. There we go. Congrats. Round of applause. All right. Now, just to show everyone else what he's done, let me just get out 2K H2SO4 K2SO4 plus H2 2K plus H2SO4 plus arrow K2SO4 plus H2. Okay, now first things first, we split up our compounds. So I see a compound there, and I see a compound there. I'm going to split those up, leaving everything else the same. So we have 2K that's left the same. My compound is going to get split there and there. The reason why I know that is because I know my H makes a positive, my SO4 makes a negative. So I know that those two were the ones that combined to make an ionic compound. Now I have two H's, and they each form one positive. And then my SO4, I only have one lot of them. They form a 2 negative. Then I'm going to draw my arrow. I have 2 potassiums. Each one is in group 1, so they form a 1 positive charge. And then my SO4 forms a 2 negative charge plus H2. Then once again, I'm going to check and see if there's anything I could cancel out from either side. I noticed that my SO4s match on both sides. The reason why I'm not canceling out my potassium, my K, is because on my left side, it's just K. On my right side, it's K+. Same thing with the hydrogen. On my left side, it's H+. On my right side, it's H2. So even though they're similar, they're not exactly the same. I can only cancel things out that are exactly the same. So my SO4s, they are both SO4 2 minuses. So I can just cancel those out. And then I rewrite it out to be 2K plus 2 lots of H+, arrow, 2 lots of K+, plus H2. And that is my final ionic equation. Let's Li, 2 Li, H2. Okay, so on my screen is this next one. I'm going to leave the one we just did at the top so you guys can sort of see the workings. So the bottom one, I'm going to circle it with, by here. Have a go at doing that. Lithium is in group 1, so it's going to form a 1 positive charge. Remember, hydrogens form a 1 positive charge, SO4s form a 2 negative charge. So on a piece of paper, have a go at doing that one. Remember, split up the compounds into its charges. Any things that you see that are exactly the same on either side, cancel them out. And then rewrite it. So the hard part is really splitting up the charges into, splitting up the compound into its individual charged ions. But the more you do it, the easier it will be, I promise. It is challenging at first. Close, Mick, nearly there, but you have to remember, even though you have 2 lots of hydrogen, and overall it's a 2 plus charge, you still have to write the charge as is, not the total charge, but like the actual, just the charge on it, and just write down that you have 2 lots of them, rather than changing the charge symbol. Yeah, so write it as if there's only one of them. So you sort of see on the last example we did, I have 2 hydrogens by here. That's an overall 2 plus charge, but I write my charge as only 1, and I just show that there's 2 hydrogens by writing a 2 in front to say there's 2 hydrogens, but each hydrogen has a charge of just 1 positive. Okay, let's go over the answers then. Right. So my 2 compounds that I'm splitting, then I write 2Li, keep that the same because that's not a compound. My hydrogen gets split from my sulfate, my lithium gets split from my sulfate. Each hydrogen has a H1 plus charge, and I have 2 of them. I only have one SO4, and that has a 2 minus charge. My lithium has a 1 plus charge, and I have 2 of them. My SO4 has a 2 minus charge, and then my H2 is just the same. Then I see what is similar on both sides, and I notice that SO4 2 minus is the same on both sides. And then everything else is written the same. So when you write this out, make sure that you don't change the charge even if you have 2 lots of them. The only way you show that you have more than one is just by changing the number in front, but just showing that the overall charge is what it naturally is. So hydrogen always has a 1 plus charge, lithium always has a 1 plus charge. Okay, so ionic equations, that is done. That it is quite challenging, so let me try to find a resource that I can link to make it so you can get a little bit more extra practice, because for electrolysis, and that electrolysis has been set by the science department as a whole, there is ionic equations on there that might be a bit difficult to understand without being able to do ionic equations first. So let me just quickly see if I could find a resource for you guys. So I found a link to the tutorial for this. I just linked it in the comment section, the chat section. It is, I tried to look at the BBC bite-sized one, but it's a bit like short. It doesn't really show the detail in the practice. But if you follow that link, there is some practice at the bottom along with an explanation again, okay? So I recognize that was a bit challenging, but hopefully then when we go on to electrolysis, it'll make a bit more sense rather than just being a bit gibberish, because the ionic equations, they are a higher tier, they are challenging stuff, but the more you practice them, the better you get, and then eventually it'll be something that you don't really have to think about anymore. Right, so have a good rest of the day, guys, and take care, stay safe, and make sure that you take care of your mental health as well.